Hello, my name is Onel Harrison. I'm a software engineer. Welcome to this How to Solve It video, in which we will walk through a programming problem step by step and maybe even enjoy some lovely detours along the way. Please subscribe and comment if you enjoy watching this video or if you learn something. I'm open to constructive criticism and feedback, so leave those in the comments. Engage with me on Twitter and check me out on Medium if you're more into reading than watching. Alright, let's go. So the problem that we're going to explore today is a problem called twosum, and it's dubbed by the programming community to be an easy problem. And so there are a lot of existing solutions to this problem online. They are coded in our favorite programming languages, all the mainstream ones. So it'll be easy for you to just search for twosum problem solutions on the web. So the emphasis of this video is on the problem-solving approach. How is it that we go from the problem statement or problem description to an obvious solution, and how do we make our way from an obvious solution to a better solution to the best solution that we know of? So let's get into it. The problem description is stated as such: given a list of numbers and a number k, return any two numbers from the list that add up to k. For example, we're given this list of numbers 4, 8, 10, 17 and a k of 18, and in this case we'd return true since 10 and 8 equal 18. And we're also given a bonus here to solve the problem in a single pass. The first step to solving any problem is to really understand the problem. Figure out what it is that we're trying to solve. And so in a problem like this, parsing the problem statement for the important information and discarding the unnecessary and distracting information is something that is a skill that's necessary to solve this problem, or to solve any problem. And we'll take a look at that. So the keyword given suggests our inputs. Right? If you think about any kind of algorithmic problem, you can think of it as in the form of an IPO diagram: input, process, output. What are my inputs? What conditions do I need to be aware of in order to figure out the steps of processing that will give my outputs? So given suggests our inputs, and following keywords like given, where we know that the inputs are coming next, we should pay attention to the type of input data as well. The word return here indicates our output, and following that word we may also identify the type of output data. Words like whether or if are indicating to us that there's some kind of condition that we need to be aware of. So in this case, our output value is the result of a condition, and so it's going to be a Boolean value. Words like any suggest that a condition needs to only be satisfied once. Right? And that's how we tease apart our problem statement in order to extract important information and discard distracting and unnecessary information. Examples are also an important part of understanding our problem. The examples we're given may mislead us into making assumptions about our inputs and our outputs. So it's important that we come up with examples that are beyond what's given, and also examples that will break any assumptions that we made upon first seeing the ones that we've been given. Take, for example, what's given here. This list of numbers is sorted in ascending order. It's also filled with positive integers. Is that all there is to my input data? Or is there more? So we want to come up with a few other examples. Examples that involve negative numbers, right? What if we got a list of all negative numbers? What if we got a list of numbers that had a mix of negative and positive numbers? What if our data isn't sorted? What if we have multiple satisfactory conditions within the data that we're given? And what if there are no satisfactory conditions in the data? So we need to come up with examples to explore all of these properties of our data to ensure that when the time comes to write our algorithm, we're working with a problem that is well understood which consequently will give us a better chance of writing an algorithm that is appropriate and correct. So by exploring our problem in that way, we have come up with a solution scaffold. We know that we can write a function that takes two arguments, has two parameters, a list of numbers. There's a mistake on this slide. That should be an array of integers and an integer k, and it will give us a Boolean value as the output. And then you might begin to think to yourself, okay, I have a scaffold, and after a little bit of thinking, or perhaps no thought at all, you might come up with the naive solution to this problem, which essentially is to loop over all the values in numbers and loop again over every other value and check to see if the numbers add up to k and return true or false depending on whether or not our condition is met. This is the naive approach because it's obvious. It's the first thing that probably comes to mind, and it's most likely not the best solution. But this is also the brute force approach, where we're trying all possibilities and testing them to see if they meet or satisfy the problem statement, or will give us the right solution. Now you might write your pseudocode like this, which really is easier to read, but depending on what your background in programming is, your solution might look like the previous one, or it might look like this one. For the remainder of this video, I will be working with pseudocode that looks closer to this one, because I think it's easier to read. So let's analyze this solution. Because we said it was naive, which means it's obvious, and probably not the best solution to the problem. If we look at the space complexity of this algorithm, it's going to be O of 1, constant time. We're not allocating any space that will grow with our input values. And our time complexity is going to be O of n squared. It's a quadratic time algorithm. And these boxes will give you a hint of, if you're not really comfortable with big O notation, they'll give you a hint for how we got to say that this is a big O of n squared algorithm. You'll see that for the outer loop, that's linear, and then we're doing another linear operation inside a linear operation, so we're in effect multiplying two linear operations, and so we get a quadratic algorithm. So after we've given our brute force approach and we've done some solution analysis, an interviewer, or you, might think, okay, there's a better approach. How do I make this better? And so you might start off with what you already have. And so here, if you look at the inner loop, if we were able to reduce this inner loop to a more efficient process, then we could make our algorithm more efficient. And in that is the assumption that we have to go through the list at least once. So it's going to be a linear, at least a linear algorithm. An algorithm with linear time complexity. And if you look closely enough at that inner loop and describe it in plain English as opposed to code, what we're really doing is searching for a number that is not the current number that we're looking at, and then doing a comparison as to whether or not that number meets some condition, or this pair of numbers meet a condition. So this is a linear search for what we're calling other number. And so you can start to think, can we make this faster? And since we're talking about search, and you might have learned that a number of search algorithms that you can do on lists or arrays, and you might think, oh, there's something faster than linear search. Maybe I can use binary search in this problem. And then you might think, but in order to use binary search, I have to operate on a sorted data set. And so you might think that maybe you should sort numbers inside your loop. And then you might step back and say, oh no, I wouldn't want to sort numbers inside my loop because that would be inefficient. I'd be doing the same thing for all the I'd be sorting a new array of numbers inside my loop for each number that exists in the original numbers array. And so you might say, okay, maybe I could just sort the original numbers array and come up with an entirely new algorithm for solving this problem. And maybe you could. Maybe you could come up with an n log n solution where you sort the numbers array, and instead of trying to search using this method, you might search by using pointers that exist at the extent of the numbers array. So the start of the numbers array and the end of the numbers array, and you might close in based on some condition. You might move those pointers in until you find a pair of numbers that meet the condition, or you reach a terminating condition and you don't have a pair, and so you return false. Maybe you could do that, but you're not much better off. It is an optimization, but there's a lot more that you could do. There's a lot more that you could do here. So let's think about what's the best possible search case and how we can get there. Right? What is the best possible search case? If I every day put my keys right beside the door of my apartment or my house, then every morning when I'm leaving for work, it's easy to find my keys. I don't have to search my room. I don't need to search any other part of my dwelling. I just need to go where I know I left my keys. So that's the optimal search case, where I know exactly where something is. And the parallel here is that we would be doing a constant time lookup. Right? We just need to look up where my keys are. Look up where other number is. Okay. So we need a lookup that we can do in constant time. And in the average case, we can do that with hash tables or with hash sets. Okay, so maybe we can use those to solve this problem. Let's go a little bit further. Before we look at how we can use hash sets and hash tables to solve this problem, let's revisit how we think about this problem, right? Or add it to how we're thinking about this problem. We know that number and other number are both going to come from the numbers list or array. We know that number plus other number equals k. And if we do some transposing and write this equation in terms of number, then we know that number is going to be equal to k minus other number, and other number is going to be equal to k minus number. Okay, so then we can look up number and other number from inside the numbers array or the numbers list. Okay. Now, if this is enough information to have a light bulb go off, then by all means, pause the video, try to solve the problem if you've never solved the problem before, and come back. But if not, Let's continue. So now that we know that we need to do a lookup from a collection that has all the numbers that are in number, and we need to do that lookup in constant time, then we might convert numbers, or not really convert, but create a new collection that's a hash set or table with all the numbers from numbers in it. And then for each number in numbers, we calculate other number, which we recall is k minus number. And if other number is in our hash set, then we've met our condition and we can return true. And so we end up with a two-pass solution. And usually we don't write the 2 in the time complexity here, but I do this to show that we're progressively getting better, because there is a better solution than this. Remember, there was a extra or a bonus to solve this problem with one pass. So this is an n plus n, a 2n solution in time complexity, and then O of n space complexity solution, because now we're creating a collection that grows with the size of our input numbers. Okay. Let this sink in for a second. All right. How could we make this better? How can we do this in one pass? Because this is two pass, because in the green block here, the second block, that's one pass over numbers. And if we expand the convert numbers into hash set or table, which is really to create a hash set or table that has all the numbers of numbers, that's one pass over numbers. It's another pass over numbers, so it's two passes. Okay. All right. What if we just built up the hash set as we went along? Would that work? Let's think about it for a second. If we had 4, 8, 10, and 16, or 17, or whatever we had in our example, and we kept going through and we just kept adding everything that we saw as we went along, and then we hit 8 and we were looking for 10 but we hadn't seen it, but then we hit 10 and we saw 8 and we thought, maybe that will work. And so there is this one pass solution where we initialize an empty hash set or table depending on the variant of the problem, right? Here, the more appropriate one, I believe, is the hash set. We do what we were doing before, and we look up if other number is in the hash set and return true if that condition is met. And if it's not met, we simply add the number that we have to the hash set and move on. And now we have a better solution where the time complexity is O of n and the space complexity is O of n. And this is the ideal solution that you will find online when you search for runnable code in your favorite programming language. So, big up yourself for making it this far, and thank you for tuning in. Again, Please subscribe and comment if you enjoyed watching this video or if you learned something. And again, I'm open to constructive criticism and feedback, so leave those in the comments. Engage with me on Twitter and check me out on Medium if you're more into reading than watching. And until next time, peace.